So I'm going to be representing the mantle group today, which is based at the University of Alberta. This was part of my work as a postdoctoral fellow at the university, and it was with Graham Pearson. Today I'm going to talk about Nb-REE mineralization in Superior and Slave Craton sources and geochronology. So today I'm the one presenting, but this is the work of many, many people that I thank today from university, but also from government and industry. So Nb-REE deposits are dominantly magmatic and believed to be sourced deep in the lithosphere. That's why we're going to talk about the mantle today. One of the questions is the source enriched by melt or fluid circulation in the mantle? We're going to talk about that with mantle xenoliths from the Elliot Lake location, south of the Superior Craton. And we're going to talk about are magmatic ore processes sufficient to create high-grade deposits in REEs and Nb, or is late hydrothermal remobilization necessary? So in this kind of deposits, we see a lot of features that indicate hydrothermal remobilization. The question is it really necessary? Is it always there? And is it disconnected in time with the magmatic event? So for that, we're going to look at Bastnaesite dating from the Thor Lake deposit located in the Slave Craton. And I'm going to highlight a new PhD project starting at the University of Alberta on diamonds. So why do we look at the mantle? So some ore deposits are directly linked to the mantle. They're known for it. For example, diamonds or nickel copper PG deposits, but some other deposits are indirectly linked to the mantle. Alkali systems, for example, some models for organic gold deposits or some models for kaolin-type gold deposits. What we are interested in is mostly the metasomatism that could happen in the lower part of the lithosphere. I'm going to take the laser pointer. Yes, okay. So in these fronts here, but also low degree melting that can transport these areas that have been metasomatized and bring them to the surface to create the crustal deposits. So we're going to look at two locations, the Elliot Lake, like I said, which is here, and the south part of the Superior Craton, and the Salt Lake deposit, which is here in the south part of the Slave Craton. We're going to start with Elliot Lake, looking at mantle xenolith. The idea here is to look at how much remobilization there was in their signature to show that there was metasomatic processes that enriched them in Nb-REE plus or minus uranium in this area, and that was caused by the major event of the mid-continental rift at 1.1 GA. So like I said, Elliot Lake is in the south part of the Superior Craton. It's right here north of Lake Huron. And the gray part that you have here is the mid-continental rift. So it's centered on Lake Superior. There are a lot of Nb-REE deposits that are located along the Lake Superior because of it. And actually, this mid-continental rift is associated to the Kiwinawan large igneous province, which is very big, as you can see. This is this whole circle right here, which englobes also the area of Elliot Lake. So this is the type of sample that we are looking at. It is mantle xenolith in an host. In that case, it's a lamprophile host that we dated at 1.1 GA, so coeval to the mid-continental rift event. And the xenolith is specifically, in that case, a spinel lazulite. So you have olivine, clinopyroxene, orthopyroxene, and spinel. The first hint to see that our samples were remobilized was the analysis that we did on olivines. So this is the one on the left here. You have the Mg number. And this is what we could expect from usual cratons. So you have all cratons here from the literature and the Slave Craton. And this is the data that we have for Elliot Lake. So already we see that this is not the type of signature that we're supposed to have, and there is more to it. On the right, we have aluminum and calcium that show us a mixing line. So in blue and green, we have the samples from our mantle xenolith. And here in purple, you have the lamprophile host. And you can see this very, very pretty mixing line between the two. So we have some melt depletion involved here that push us to the origin of the diagram, and we have a lot of influence from other magmas that are around. We can also see it with PGEs. PGE stands for platinum group elements. So we have osmium, iridium, etc. Here I've put our samples, so also in blue and green, the lamp profile, but also two typical patterns. First, the typical pattern for melt depletion in red here, with typically a low palladium that we also see in our samples, so there is some amount of melt depletion, but also the typical metasomatic pattern where you have an enrichment in rhenium, which we also see in our samples. So this is really a combination of the two. And this cannot be only due to the lamp profile host's metasomatism, because some samples are even higher than that. We looked at the composition of clinopyroxenes to try to understand what kind of metasomatism we're talking about. Here we have titanium, europium, and lanthanum, ytterbium, and we have two fields defined in the literature. The blue ones seem to indicate silicate metasomatism, and the carbonatitic ones are in green. But overall, as we've seen before, it's kind of a mixing line, so we don't really restrict ourselves to say that those ones are only silicate metasomatism and the other ones are only carbonatitic. We think it's a kind of an in-between of silico-carbonatitic metasomatism overall. What is really interesting is that this signature is also associated with enrichment in some metals, specifically rare earths, in that case lead, niobium, and uranium. What is interesting in this figure is the green part. So we have the different minerals, olivine, autopyroxene, clinopyroxene, and the green one is the whole rock. And the covered area is what we would expect for spinal peridotites. So you can see that we are above what is expected, and this is due to the metasomatism of our samples. If we look at our samples, but also other rocks from the literature, for example, so here we have in black, the mantle xenolith, in green, the lamp profile, in red is kimberlites, and in blue, marids. So we can see that we have a lot of trace elements here and some enrichment compared to the depleted mantle. What is interesting for us here is rare earths and niobium tantalum, and you can see that you have a lot of enrichment for these samples that are either low-degree melts or metasomatized rocks. And we clearly believe that this is creating these enriched sources that are then transported to form the crustal deposits. So this is our main conclusion from this study, that silico-carbonatitic metasomatism created this source, and then low-degree melts transported them to the crust. The second part of this talk is about Thor Lake Bastnaesite dating. So Thor Lake is one of the biggest rare earth deposits in North America. The mineralization has not been dated yet, only the main intrusives. So that was really interesting for us to try to do that. Thor Lake is located here in the Northwest Territories in the south part of the Slave Craton. It's associated with alkaline rocks, specifically cyanides. The main ore minerals include rhodolite, xanthim, gadolinite, monazite, and rare earth carbonates, including bastnaesite. So this is how it looks like. You have the mineralized zone. There are different paths to this mineralized zone included in the Thor Lake cyanide, and around it you have the gray slate granite. The intrusive complex overall has been dated at 2.1, 2.2 billion years. This is the kind of sample that we have. So this is this big chunk right here. There is pretty much two minerals in this chunk. It's in white you have quartz, and in red you have bastnaesite. Bastnaesite being the rare earth carbonate. So it was not really difficult to find the mineral of interest. Bastnaesite was a phase of replacement. So if you look at the synth section here, for example, here you have the form of an ghost mineral that was completely replaced by plenty of little needles of Bastnaesite. So we know that this is not the primary rare earth mineralization. Unfortunately, nobody seems to know what was there before. And Bastnaesite comes as an hydrothermal mineral replacing all of these phases. So this is the composition of Bastnaesite. This is so very elevated in rare earths. And this Bastnaesite in our samples is starting to being altered into parasite. So the main difference between the two is the amount of calcium that we can see here. So it's going to be our main tracer of whether or not our mineral is altered. Here you have a map of the side of a grain, where you can see that actually this big grain that we've seen is actually plenty of little needles of Bastnaesite and partly transformed into parasite. In the inside, it seems to be a little bit more altered, so we tried to target the needles that were on the outside to make sure that we have something that is the closest possible to something that is not altered. If we compare the rare earth pattern between Bastnaesite and parasite, it's quite similar. It's just very enriched in light rare earths. And what we were interested in also was understanding if, during the alteration, do you mobilize uranium, lead, and thorium, which would be a major issue for dating in our case. So this is not really the case. Here we have two factors. You have uranium here, thorium, lead, all against calcium. And you can see that you have some variation due to the zoning of the grain, and some variation due to the alteration, but most of it is actually due to the zoning. The zoning in uranium, lead, thorium is actually very well known for carbonates in general. There are some examples in the literature in the great paper of Roberts and collaborator in 2020. You can see that in carbonates you can have very different variation in grains, like exampled here. The idea is to make a line of spots in that zoning, like they show here, to be able to form this line in Talwasserberg and have your age. So this is the main method to be able to date carbonates these days, and this is what we try to do. So we try to have a matrix match standard, of course, reference material. There is only one in the literature, which is named K9. So we used this one. It's at 116 million years old. And we also used another one, a carbonate marine calcite cement, WC1, at 254. Unfortunately, they're not very old. So we're trying to date supposedly something that is 2 billion years old. But this is the best we could get. So this is all the, so all of them is an integration. This is all the ellipses that we got for the Bastnaesite dating in Thor Lake. So you can see that this is not one single population here, obviously. So we have here all the ellipses with variable calcium content, because even if we try to target only low calcium areas, well, there's always some surprises when you ablate. But this is really interesting in the end. So we have a lot of trends. We can see already one like this, and there seems to be something here that is close to the Thor Lake cyanide age, so the main intrusive that is linked to these Bastnaesites. When you decompose all of this, actually with the calcium content, so here I've indicated calcium just in counts per second extracted from the ICP-MS. So here we have low calcium. I've taken this value because this is the value of the standard, and we know that the standard is a Bastnaesite. So I've decided that this value is the threshold to say, okay, this is just a Bastnaesite. There is no alteration whatsoever. We have two ages, one at 2 billion years old, which is a little bit younger than the intrusive, but close to it, right here. And the second one here, that is at 1.7. So this is already a lot younger than the intrusive, and seems to be a first event for the very clear Bastnaesite. And what is really interesting is that the more calcium you have, the more you seem to have a young age. And here you have an intermediate calcium content, and you have an age of 1.70, before it was 1.77, so a little bit younger. And when you have very high calcium, so this is clearly parasite, you have all of these ellipses that go towards 865 million years. So this is really interesting to see that in a place where that was dated at 2.1 billion years old, you can also have the mineralization sometimes that dates at 800 million years old. So this is really a question of how you can explain that much remobilization for all that time. Here you have the four groups. So the one here that was at 2.0, so close to the intrusive, this is the one here. Then you have the yellow one that was on 1.17, the blue one on 1.7, and this one, the youngest. We tried to find events in the area from safe craton that could match these ages. It's actually not very easy. If anybody in the room has ideas, I'm taking them. There's nothing that seems to really overlap. There is the Great Slave shear zone that is nearby, so we think that maybe this could be just the reworking of this. The Talton-Tellen peak metamorphism is a bit disconnected, and we also have magmatic events, dike swarms, but nothing really overlaps, and even more for the 800 million years old one, nothing really exists in the literature, it seems. So this is really new information, and we're still thinking about what this all means. So this is the highlight for Thor Lake. So the carbonate dating setup seems to work perfectly. Thor Lake is definitely not the best candidate for a standard, unfortunately. We have 4 main ages, which we are still trying to understand. And so it's definitely the mineralization is definitely a lot younger than the magmatic source. So the main common features between Elliot Lake and Thor Lake is that both have the impact of fluids, and this could be the cause of enrichment. This is pretty much the highlight. And before finishing this talk, I want to also talk about the new project of Andrea Pezzera. He's working on Mesoarchean diamonds from Manitoba. So this is Andrea on the right here. I hope he likes the photo. So he started his PhD maybe a year ago now, and he's going to work on these unconventional diamonds. So these diamonds have been extracted in the Mesoarchean. So they lived very shortly in the mantle, which is the main highlight of these diamonds. So they are at 2.8, 2.7 billion years old. And there are only 3 other occurrences in the world of Mesoarchean diamonds, which are Tree River that we have here, Wawa, and the Witwatersrand. And so his location is right here in Nb-REE Lake. So in these diamonds, they found 2 kinds of inclusions, the olivines and the amphocytes. So the main work was to construct the geotherm for these diamonds. The temperature estimate is from nitrogen aggregational state of the diamonds with FTIR, and the pressure estimate from the residual trapping pressure of the olivine inclusion. Overall, this geotherm here is really cool. This is similar to what Suzette Timmerman has found in the Slave Craton, and seems to be a common feature for these Mesoarchean diamonds, so this is really interesting. Also, the presence of amphocytes shows high pressure, low temperature metamorphism, which could be testifying of active subduction. So this is it for me. Thank you.
I noticed
Honestly, I don't think I can. I'm not familiar enough with this kind of. Really, I was focused on the dating. I honestly have no answer for you. Sorry.
I don't know either, but usually hydrothermal
Mm-hmm.
will have commonly positive geologic so
I will look into that.
the question.
What is the source of the fluid that metasomatize the mantle? Is it coming from below? Is it deeper? Or where is it coming from?
I don't think it can come really deeper because we're supposed to be really at the base of the lithosphere already. If we compare to the samples that were found, for example, from other people in my group, I don't think it comes from deeper. But we don't have a lot of constraints on this because we also tried to look at how deep we were with our samples, but there is so much remobilization that it was given so many different information at once that we couldn't form a single conclusion for it. I don't have really an answer for that. I don't think it does, but I have no strong evidence for it.